Hey BC, hope the test went well. This is an intro to the homework for the weekend. This weekend, you're going to be doing some of the intro stuff and the early stuff involving a thing called parametric functions. This is something we normally cover in Honors Pre-Calculus. They didn't get to it last year. So I'm doing a short video to describe them to you and show you how to work with them a little bit. And then you'll be able to go to the AP Classroom videos and use those just fine. So parametric functions, here are the goals. We want you to understand just what a parametric function is, have some idea of why they're useful, and go, oh, those look pretty good, and then be able to use your calculator to work with parametrics. All right, so have your calculator nearby because you're going to need them for this problem. So if you, it says first question, and there's some physics in here too. And if you have questions about about the physics, I'd be happy to talk about it with you when I get back if you have questions. But you don't need to know any of the physics. So, you can just kind of trust me on some of the equations that I'll give. It's not necessary for you to know those equations. I just wanted to give a real life example so you could kind of see that, oh, parametrics make sense. Like, that's a pretty cool thing. Okay. All right. So if you pass a hockey puck on a frictionless surface of ice at 76 feet per second, what's its position at any time t, starting from 0? And this is not a calculus problem. This is a sorry about the shadow here. Oh, that's weird. So this is not a calculus problem. This is just an algebra problem. And so we'll call it the x position. So because it'll be like sliding along the ice, right? That its x is going to be 76 times t. There's no friction, infinitely long surface. So after 1 second, it'll go 76 feet. After 2 seconds, it'll go whatever, 152. Now, second question, if you throw a ball straight up at 44 feet per second, what is the height of the ball at any moment in time? Sorry, I left off the end there. And this is an old equation from Mr. Engel. We call it h of t, but I'm going to actually call it y of t for reasons that will be clear in just a little bit. And it's equal to negative 16t squared plus 44t. You studied this equation a little bit in Algebra 2, Honors Algebra 2 Trig, but you're not required to know it. So just trust me on that. So if I go on the ice, I've got an equation. If I throw it straight up in the air, I've got an equation. Now, what if I combine these two things? So what if I throw a bag of peanuts at an initial velocity of 88 feet per second at an angle of 30 degrees? Turns out you can break this thing up into two parts to it. There's a horizontal part. There's a horizontal thing happening, that this thing is being thrown somewhat horizontally. And there's also a vertical thing happening, that this thing is also being thrown somewhat vertically. And I've made it, just to let you know, that I've broken it down. And remember, you don't need to be able to do this. This is just for motivation to make the problem look cool. I've broken it down so that this is about 76 and this is 44. So I was like breaking this down into two small parts, and that's what we introduced up above. But now I'm giving you the real problem. What if we're throwing it and we throw it at that initial height of 30 degrees. Gotta sneeze. Pause. So what I'll let you know is that you can actually, in physics, again, you don't need to be able to do this, but you can break this into what's happening horizontally and what's happening vertically. Like gravity is affecting it vertically. That's why we have that negative 16 equation, t squared equation thing. Gravity is affecting it vertically, but gravity isn't affecting it horizontally. And these are like two totally separate worlds. So the question is, what is the question? The question is, describe the path of the peanuts. So what we could do is we could use these equations up above. This is going to tell you what the x position is. This is going to tell you what the y position is. So we could plug 1 in for x and 1 in for y, and that'll tell us what's happening after 1 second. And then we could plug 2 in for x and 2 in for y, and we could find out what it was at that moment. Now, we're going to do this on the calculator. And so bring out your handy dandy calculator. And in order to do parametrics, though, you need to hit the mode button, and then you need to find parametric. We're going to switch the mode of the calculator. So on the 83 or 84, it'll be par, P-A-R. Right, cool. So what's different now? Well, I want to enter this equation, and whoa, look at that. So it's got the x and the y defined separately. And so I can type in 76t for my x, and one cool thing here, notice this button here, the x button that we always use, it says x comma t. If I hit that button, now it gives me t's. So it's like, oh, okay. So these are different modes. And depending on what mode I'm in, it gives me a different letter. That's why there's 4 things here. Cool. So now we've got this. Now we're going to hit the window now, which is also going to look different because now, like in the old days with a regular, with function mode, the way it makes a graph is it goes from left to right across the screen and it makes 1 point for every pixel and then it connects the dots. But now X and Y are both based on this other variable T. So we're first going to say, all right, we're going to start time at 0 and we're going to end it at this. This is just what it happened to be set at. You'll notice it's 2 pi. It's not relevant. It's not going to matter for us. It'll be off the screen by the time it hits 6. And then T step is, okay, how much should you advance? Like it's going to start from 0. It's going to end at 6 point something. But how much should we go up each time we wait? We don't have pixels here because we're just operating on time. And so I made the T step 0.05 so that every 5/100ths of a second, it's going to plot a point and then it'll connect the dots. If you make this a larger number, it'll make fewer points. So it'll graph faster, but it'll have less definition. If you make T step really big, like 1, it's only going to graph like 6 or 7 points and then be done. Or maybe 8, maybe it'll graph 6.28, I don't know, but very few points, and it will connect those dots, and you'll get a really rough look at what this thing looks like, and it wouldn't be very helpful. There's no set value. You might have to play around with it given the problem you're working on. And now the X's stand for literal X's. We're watching the bag of peanuts fly through the air, and the Y's stand for the vertical dimension. Okay, so cool, we've got it. Let's hit graph. And I think I already graphed it, so that's why it just did it really fast. And there it is. There's the peanuts flying through the air. And you can see it was making some kind of parabolic thing. And I can trace it. And when I hit trace, then notice how it's moving every 5/100ths of a second. It's jumping pixels because it's going based on seconds, not based on pixels, not based on X. And it plugs it into each function. It gets the X and the Y, and it just connected the dots. So cool. All right. So, so you get a graph. It seems like I could have done this with a parabola. I don't know why I need this thing. Aha. Okay. Let's get to the next one. So all you need on this one is just like, it's going to go from 0, 0, and it's going to go, whoa, right? Okay. So now a wind gust comes up, and just as you throw it right in your face at 20 feet per second, what does the path look like now? So I'll show you how this works. So I'm going to y equals, now you don't need to know the equation, right? Remember that? So, but now it's going to be 76 minus 20t because 76 minus 20t. I got to hit that. I can't hit the t button. And then parentheses. Oh no, I need to back that up. Delete. I need to put that in parentheses. And we're doing good on time. We're doing good on time. Excellent. Okay, good. Looks good. And then I need to have it times t. There we go. Just a quick thing on this. So like after 1 second, instead of the velocity being 76 feet per second this way, it'll be 56 feet per second. And then after 2 seconds, it'll be down to 36 feet per second. Like if this wind was blowing in your face and you throw it, that wind, and the wind is blowing perfectly horizontally, then the wind is going to slow it down horizontally. But the wind doesn't affect the Y because that's being affected by gravity, right? The wind is going straight this way. That's not going to affect up and downness. That's only going to affect left and rightness. The point of doing this example is for you to see, by separating the left and rightness and the up and downness of this thing, then I'm able to control each one of them individually. And so I have more control over where this thing goes. Okay, cool. Sorry if you hear voices in the background. I'm at my stepmom's house. My stepbrother and my niece are here. So, okay, I think I'm pretty good. You ready? You ready? All right, here we go. Oh, and it curved down. Now your calculator should be a little bit slower than this one. I think it's kind of fast because it's a computer, I want to see it fly through the air. So I'm going to change it to 0.01. So now it's going to graph a lot more points, but I think the computer's just too fast, doing it on this thing rather than on a real calculator. And then I want to change the line. Yeah, I want the ball flying through the air. Yeah, definitely. That is what I want. I have to hit OK. I can't use the mouse. There we go. Okay. You don't have to do that. I'm just having fun. All right, here we go. And let's watch it. and the wind is blowing, the wind's blowing, the wind's pushing back, and it goes, whoa, the wind's starting to push it backwards. Now it runs out of horizontal velocity, and the wind starts pushing it backwards, and it ends up coming back. And that's what the bag of peanuts does because the velocity is so strong. All right, it's still graphing points right now. You can see that right here, but that's because it's going all the way to 6.28 seconds. So, it's going to have to keep going until it gets there. If you ever want to stop a calculator from graphing, you can hit enter, which pauses it. You can see it's still kind of going right here. That's a pausing of a graph, but that doesn't help me here. If you hit the on button, that'll just stop the graph. Right? Because it was still doing points while it was down in the bottom of the earth there. All right, and so you can see how we were able to control it. You can make it, go up and then go back that way too by having a really strong wind. But anyway, it was just kind of a fun problem. So and so now instead, it looks like that. Yeah. All right. So going back to what the purpose of this was, I wanted to review for you what parametric functions are. They're functions defined by x and y as functions of some other variable, typically t, because that's like time passing by and you're watching something happening. So that's what parametric functions are. You might be wondering right now and say, wait, Mr. Ellinger, it does not appear to be a function because the vertical line test, that last graph. But remember that they're functions of time. So x and y are functions of time, and its location is a function of time. At any one moment in time, the peanuts were only in one place. But you're right, y is no longer a function of x for this problem. I want you to have some idea of why they're useful. Hope it worked. And then I wanted you to be able to use your calculator to work with parametrics, because I wanted you to see where those buttons are. Okay? That's the intro you really need. At this point, I'm going to send you off to AP Classroom. I got stuff I'm doing here, and I can't record videos for everything. So I think the guy's very clear. He sounds a little smug to me, but he's very clear, and I think he has his heart in the right place. He just seems like kind of a know-it-all. I don't know. Maybe you guys could tell me what you think. That's my take on this guy. But I think he's really clear, and he's got a lot of experience, and he does a good job. Yeah. Okay, so I think that's it. So you're going to have some AP Classroom videos on parametrics, and then I hope I'll actually be back in time for class on Wednesday of next week, because my flight comes in the morning on Wednesday, and so I hope to see you then. That would be wonderful. I'll have some kind of emergency backup plan in OneNote, but I hope we don't have to use it. Okay, that's it. Take care. Again, I hope the test went well, and I will see you next week. Bye-bye.